Welcome back to geometry. We want to continue taking a look at section 27, non-Euclidean geometry. And we want to take a look at our second and last non-Euclidean geometry, which is hyperbolic geometry. For this geometry, we don't have quite the nice visual aid to understand it. And what we'll do is we'll take a look at a few models. And when we look at these models, I'll just give kind of a rough sketch of them and show what it looks like for 2 points to be on a line. But we have a few models for this. But before we get into that, what I really want to emphasize is that for both hyperbolic and spherical geometry, both of these result because they fail Euclid's fifth postulate. And the consideration is just how can we fail Euclid's fifth postulate? So in Euclid's fifth postulate, what it is it says we have, for a line and a point, we can find a parallel line, a line that's parallel to the given line through the point that's also given. And that line is unique. So how can we fail that? Well, there's two ways to fail it. One is the case where there are no parallel lines at all. Like spherical geometry. The other way that we can fail Euclid's fifth postulate is if there's not just one parallel line, but there's an infinite number of parallel lines, or more than one, rather. We would find that as soon as we assume that there's more than one, there's actually an infinite number of them, which is something that we won't dive into in this course, but is something that's quickly discussed in many courses, which do spend some time on non-Euclidean geometries. So let's take a look at our notes. Keep in mind here as we look at them, there is some material that you should take a look at, which also introduces hyperbolic geometry, much like I was just saying. But we'll go ahead and start here at axiom 17, where we're saying, all right, if we've got the first four postulates of geometry, once we get to that fifth one, if it's not the Euclid's fifth postulate, what is it? Well, we could say this one instead. We could say that it fails Euclid's fifth postulate, and that given a line L and a point P, there is more than one line parallel to L that contains the point P. And this is hyperbolic. This lands us in the space of hyperbolic geometry. And when we look at our examples of this, our models of it, there are a few terms that we need to be familiar with. And one of them is that a model is conformal if the angle measures in that model look right. So if angle measures are actually preserved, then that's called conformal. We just have to understand what it means to preserve them, or to actually have them be right. And two circles or arcs are orthogonal. Now, for those of you that have taken Calculus 3, you know that orthogonal is another way of saying perpendicular, but it's right. It's not just the conversation about lines. What it is if when they intersect, the tangents are perpendicular, right? So and that's exactly the same definition here. So two circles are orthogonal if where they intersect, then the tangents to the points. Then the tangents to the circles at those points are perpendicular to each other. So if I have a circle and another circle, then where they intersect, right, we're saying that the tangent line and the tangent line form a 90-degree angle. They're perpendicular to each other. That would be orthogonal circles. And we would find that if it's true at one of them, then it's actually true at both. So we would have this situation as well. Okay. And then, much like was said in the previous video or a couple videos ago, by plane, we simply mean all the points in the geometry. So let's take a look at, we'll look pretty well at these first three models, the Poincaré disk model, Poincaré half-plane model, and the Beltrami-Klein disk model. So for the Poincaré disk model, this model is conformal, so the angles look right to us, but the distances are distorted. So when we look at the Poincaré disk model, what we have is we're taking the disk centered at 0 or wherever, doesn't matter, but we're considering a Euclidean circle, and it's all the points in the interior. So we're actually not including the exterior of the circle. So we would maybe want to use a dashed line for that. So there is our disk. And the lines in the Poincaré disk model, the lines are either diameters or arcs that are orthogonal to the boundary of the disk. Okay. So if I've got 90-degree angle there, right, they meet orthogonally. This is also a line in this model. Okay. So these are the lines in this model. So if I have 2 points, A and B, right, if I were to connect them with a straight line, it's not a diameter. So they're not connected by that straight line. They would be connected by the arc, which is orthogonal to the boundary. Okay, so those 2 points are connected with this line. So that's kind of interesting. And then if I wanted to talk about how lines intersect, and I wanted to talk about their angles, since this is conformal, it does preserve the angle measures. I would look at the tangent, and I would look at the tangent, and then this angle measure is actually the angle at which those 2 lines intersect. Okay, so that's the Poincaré disk model for hyperbolic geometry. Something that's interesting is that as you get closer to the edge over here, right, it goes on forever and ever. So as you get closer and closer and closer to this edge, very small movements are very large distances. And the closer you get to that boundary on the outside, the larger a movement is. So this much, the distance, the length of that line right there is much shorter than the length of the same drawing over here. Okay, this line would be much longer because it's closer to the boundary. And that is highlighted in how distance is calculated. And I'm not going to worry about the distances, but the point is that if we were to consider this line with endpoints P and Q, then you could calculate the distance based on, I believe, the Euclidean distances between these points, plugging those values into the natural logarithm, and the output you get is the distance between the points in this particular model. All right. Oh, sorry, that was up here though. Same thing though. All right, so then we also have the Poincaré half-plane model, which has essentially the same collection of, or what you can think of as, well, some of you might observe this as being the same collection of lines in this model. So the Poincaré half-plane model. So these are all the hyperbolic geometry. These are different ways that we can represent the geometry. In Euclidean geometry, it's just a plane. It goes on forever. It's flat, right? The flat earthers are in heaven with that. Cool, awesome. Euclidean geometry. It's what works out very nicely when we're writing on paper. But the reality is right, the Earth is round, so that's actually more like a spherical geometry. And then here, so the sphere is a great model for that. And then we have this geometry, which is just a little bit more difficult to understand. And these are simply models of it. And we're not going to spend, again, we're not spending a lot of time here. But you might notice, to maybe emphasize the parallels. If I were to consider this point here, call it C, here's a line, and I can have a whole mess of lines that pass through it that do not intersect this line. So all this line and that one pass through C right there, but they don't intersect this diameter, so they're parallel. They're passing through C and parallel to this line L. Okay, so we can see that there are multiple parallels. So the half-plane model, what does the half-plane model look like? Well, in the half-plane model, what we're doing is we're taking you can think of it as the top half of the coordinate plane. And lines here actually look like either vertical lines, okay, these are lines, or what you have are half circles. Notice that they also, because they're a half circle, they also intersect orthogonally to this blue dashed boundary line. So if I wanted to, certainly I could consider this to be my line. Let's see. I'll try to find a good way to go about this. If I wanted to talk about, well, distances first of all, let's say that we've got A and B. So if I have A and B, since they're not vertical of one another, the line that contains them both is going to be the half circle that contains them both. And there is only one half circle that would do that. Is that right? That should be right. But then we want to say, what about there being an infinite number, or at least multiple parallel lines through a given point? So I want to be careful about this. And let's see here. Yeah, one way that I could do that to try and keep things simple is if I consider this my line L and make this my point C here, then I could take any circle with a large enough radius that it doesn't intersect L. Okay, so any circle with large enough radius. There's a line through it, but I could take a slightly smaller half circle. That was quite a bit smaller, and that's okay. And there are a lot of different half circles that I could use. So there's multiple lines passing through C that do not intersect L, so multiple parallels. All right, and then I suppose we didn't really, we showed the line passing through A and B, but we didn't talk about distance. It's the same conversation about the natural logarithm of these distances. Yeah. Which is discussed here again as well. Okay, So those are the two models so far, the half-plane model and the disk model. So kind of interesting. All right, so the next model that we'd like to take a look at is the Beltrami-Klein disk model. I'm sorry, I didn't mention this, I don't think. In the Poincare half-plane model, it is conformal, so the angle measures do look good again, and those are measured in the same way. Angle measures are determined by considering tangents at intersection points to find the angle measure. All right, so for this one, it's not conformal, and so that's not quite as nice. And neither is our last one, but the Beltrami-Klein disk model also takes a plane, but we simply say that the lines are the chords of the plane, disk. The plane in this case is again the interior of a circle, so it's a disk, and lines are the chords. So this is the Beltrami-Klein disk model. And this one isn't quite as fun. The lines in this case are simply the chords. So it is straight. It is a straight line model. Okay. So this would be P and Q, and I think distances are calculated in the same way again. And of course, if I wanted to talk about some point C, then I have a large number of lines passing through C, which do not intersect this one. So we have a line, a point, and a large number of parallels. So that one's a little bit less interesting. The common models are the Poincare disk model and the Poincare half-plane model. And then the hyperboloid model is you could simply plot this in GeoGebra or your favorite place and get a 3D model of this. And then distances are just the length of the geodesic on the surface. And that's really a conversation for a differential geometry course. Not something that we want to do here. That's more of a graduate level course, but this is an interesting model as well. And the last thing that's discussed in, I guess a few more things. I'd encourage you to take a look at this this example, investigate that, and let me know if you have any questions. So go ahead and try this example. Find the distances that are discussed here, and then feel free to take a look at this website and follow along with these. I'd like to share with you, though, the conclusions that we get, or that you should find from following that investigation. So in hyperbolic geometry, we already discussed this. There is more than one line that's parallel to a given line in a given point. Okay, that's exactly what the postulate is that brings us into hyperbolic geometry. So everything from section 15 would be false because of that. So the angle sums for any triangle, instead of it being greater than like it was in spherical, in this case it is actually less than 180 degrees. And then the amount that a triangle's angle sum differs from 180 is called its defect. It's denoted by delta. There are actually, right, in spherical geometry, we said that there are no parallelograms. Here we take it a step further, and we, or at least relatively specifically, because we can have parallels, there are actually no rectangles. No rectangles. So I'm sorry, it's not a step further, it's actually a slight refinement. We allow for parallelograms, but we can't have the one where it's for 90-degree angles. All right, for hyperbolic geometry, angle, angle, angle is in fact a congruence condition. So that's kind of interesting. It's not just a similarity, it is stronger than that. It is a congruence condition. And the area of a triangle is proportional to its defect. So a large difference from 180 means that the area is larger. So larger triangles have smaller, you would think it'd be smaller angle sums. Smaller? My notes say larger, so I'm thinking that there's a discrepancy somewhere, but not terribly important. You could confirm the correct answer in many places. My apologies for not having that right in front of me. But there is an upper bound on the area of a triangle. And smaller, this says, it can't be, this has to be larger in order for A and C to be correct. Smaller triangles look more like Euclidean triangles in that their sums are closer to 180 degrees. So larger triangles have larger sums, larger angle sums. Oh, actually, no, yeah, no, we probably did have that one right. Smaller triangles look more like Euclidean in that their sums are closer to 180. If larger triangles have smaller sums, then smaller triangles would have larger sums, and that would make sense because if we're always less than 180, we'd have to increase to get to 180. So if we're increasing smaller triangle increasing to 80, larger triangle decreasing. So larger triangles have smaller angle sums. Okay, yep, I like that. That works for me. But that's it, right? There are no actual problems, so please do make sure that you take a look at this website and follow these. And if you want to take a look at that in lecture tomorrow, that's absolutely fine, or in office hours or something, stop on by, schedule an appointment rather, and then make sure you take a look at this example as well. Okay, so thank you for your time and your attention. That's it. That's the end of things for now. So I will see you all again soon. Have a great day.